Hello and welcome back to part 2 of section 4.7. Today we're going to look at composite functions. Now if you think back to section 1.9 when we talked about composite functions, in order to have an inverse function, if we were to take the inverse of f and plug it into our original function, we would get x out as a result. Likewise, if I took my original function, plugged it into my inverse function, we should also get x as a result. If we keep this thought in mind, then we can apply this to our inverse properties of trig functions. And you actually have a table in your book. It's on page 347. It comes through a little bit clearer or neater maybe than what I have here in my PowerPoint. So if you want to reference that on page 347, there is a table, but essentially what we're going to look at is if our x values are going to be between a negative 1 and 1, and our y values are going to fall in between a negative pi over 2 and a positive pi over 2, then if we take the sign of the inverse sign, we're going to get x out. Likewise, if I take the inverse sign of the sine function of y, I'm going to get y out as a result. Same thing's going to happen with cosine. On this, again, I'm on a domain from negative 1 to 1 and a range from 0 to pi. If I take the cosine of the inverse cosine of x, I'm going to get x. If I take the inverse cosine of y, I'm going to get y. And again, this is going to happen for tangent. So if x is a real number, and because remember on our x values we have no restrictions, a set domain. So really we're only concerned with our y values. So if we're looking between negative pi over 2 and a positive pi over 2, then the tangent of the inverse tangent is equal to x, and the inverse tangent of the tangent of y is equal to y. Now before we go on and do an example, I do want you to keep in mind that when we're dealing with trig functions, the inverse properties do not apply for just any old value of x and y. Our values have to fall within appropriate intervals. Okay, and what I mean by that is if I go to take the arcsine of the sine of 3 pi divided by 2, this is really the same thing as saying the arcsine of a negative 1 equals a negative pi over 2. I can do this right here as long as I call it a negative pi over 2. But a negative pi over 2, if you think about it, let's look at our unit circle. Negative pi over 2 is going to occur right here. And as silly as this seems, a negative pi over 2 is different, when we're talking about inverses, is different than a positive 3 pi over 2. So even though negative pi over 2 and 3 pi over 2 fall in the same spot on our unit circle, they are not the same or equivalent even when we're talking about inverse trig functions, because 3 pi over 2 does not fall within my given domain and range. So let's go ahead and look at our example 4, which says find the exact values if possible. And we're going to start out with A. Part A says find the exact value of the tangent of the arctangent of negative 14. Well, essentially our tangent and arctangent are going to cancel, because when I take the tangent of the inverse tangent, I'm going to end up with a negative 14. And because negative 14 falls within my given domain of all real numbers, then I can go ahead and say that this exists. Likewise, for part B, I'm going to take the sine of the arcsine of pi, and when I do this, my sine and my arcsine are going to cancel, leaving me with pi. However, my domain on pi is really going to fall in between a negative 1 and a positive 1. Now, if you calculate out the decimal value for pi, it's 3.14. 3.14 does not fall within this domain, therefore this does not exist. Likewise, when I go to take the cosine of the arc cosine of 0.54, cosine and arc cosine are going to cancel. That's going to give us 0.54. And when I look at my domain for cosine, I know that I'm going to be in between a -1 and a +1. Therefore, 0.54 falls in between -1 and 1, so I am okay to keep that value. So now it's time for example 5. Example 5 says to evaluate the cosine of the inverse tangent of a -3/4. When you deal with a problem like this, I can't just say cosine and arc or inverse tangent are going to cancel out because it's not taking the cosine of the inverse cosine. I'm going to actually have to set up a right triangle and look at how my side lengths and my angles are being compared to one another. So to do that, I'm going to sketch a right triangle. And when I sketch my right triangle, I'm going to start out by using my inside function first. Now my inside function tells me that the tangent of x equals a -3/4. And I know that tangent is really y divided by x, so that tells me that my y value then is a -3, so I'm going to go down a -3 units, and I'm going to go over 4 units. So my right triangle then is going to look something like this. And this angle here, because I'm dealing with tangent and I want my opposite divided by my adjacent side, that's how I know I'm dealing with this, because -3 is opposite, 4 is adjacent. This here is going to be my angle x, which is equal to the arc tangent of a -3/4. So based on the side lengths that I've just generated in my -3 and 4, I know that my hypotenuse right here, or h, is equal to the square root of 3 squared, which is 9, plus 4 squared, which is 16, which gives me the square root of 25, or 5. So this length here now is 5. So I've used my inside piece right here to generate this triangle. Now I can take the cosine of x, which is what I just called this angle here, and cosine is equal to the adjacent, which would be 4, divided by my hypotenuse, which is 5. So I was able to identify the cosine value just based on using the inside stuff here to make this triangle. And I'm going to do this again now for part B. Part B says that we need to evaluate the sine of the inverse cosine of 2/3. Well, this here is really the cosine of x equals 2/3. So when I go and I draw my right triangle, cosine is equal to adjacent over hypotenuse. So if this right here is angle x, my adjacent side is going to be the 2, my hypotenuse is going to be 3, and I want to find this length here. Well, that length is going to be equal to the square root of 9 minus 4. So that's going to give me the square root of 5. And again, I got all of that because of this piece right here. Now I need to find the sine of x. So I can say that the sine of x is equal to my opposite side, which is the square root of 5, right here, because the side opposite of this angle is the square root of 5 divided by my hypotenuse, which is 3. And this right here then would be my final answer. And last but not least is example 6. Example 6 says to write each of the following as an algebraic expression in x. So because we're writing in an algebraic expression, that's okay to get something like x plus 1 with no equals to sign, or not to get a exact number. That's what an expression is it does not have to be an exact number. So again, I'm going to start out with a that says secant of the inverse tangent of x. I'm going to start out by using this side, or this stuff inside of the composite function in a right triangle. I'm going to identify this angle here as angle theta, and theta is going to equal the inverse tangent of x. So when I go to find my tangent, I know that tangent of y equals x. And this is really x divided by 1. And tangent is equal to my opposite over adjacent side. So the opposite side from this angle is going to be x. My adjacent side is going to equal 1. And based on that information, I can find my hypotenuse. My hypotenuse is going to equal the square root of x squared plus 1. So based on all of that information, I can now go and evaluate secant. So I end up with this secant of, we'll call it theta, is going to be equal to 1 divided by cosine. Or when I think about it in terms of my side lengths, cosine is really adjacent over hypotenuse. So secant must really be hypotenuse over adjacent. So my hypotenuse is going to be the square root of x squared. Here, let me write this down here. So I end up with secant theta is equal to x squared plus 1 underneath the radical, divided by my adjacent side, which is 1. So this is just equal to the square root of x squared plus 1. And for part B, it will be a similar process. I'm going to start out with a right triangle. I'm going to identify this angle here as theta, which is really equal to our inverse cosine of 2x. So based on that, I know that the cosine of theta is equal to 2x. Cosine is equal to adjacent over hypotenuse. So when I identify my side lengths of this right triangle right here, this is really going to be 2x divided by 1. So my adjacent side is 2x. My hypotenuse is 1. And that makes this side length here the square root of 1 minus 4x squared using the Pythagorean theorem. So now when I go to find my tangent of theta, tangent is really equal to the opposite over the adjacent, or the square root of 1 minus 4x squared divided by my adjacent side, which is 2x. And this right here then is my final answer.